kids, today we're going to do a paper 2. It's from November of last year, time zone 1. Just so you know, to make the video shorter, I pre-wrote a lot of stuff. Okay, so number 1 says, a methanoic acid is the first member of the homologous series of carboxylic acids. So what is meant by that? It's just the definition. Remember, members of the same homologous series are in the same chemical family, and they only differ by the number of CH2 groups. I would say that you had to say both of these things, even though it's 1 mark. When we get to class tomorrow, I'll let you know if I make any errors or anything along the way. Let me just make sure the autofocus is good. Okay. Next for part B is calculate the percentage by mass of oxygen in the methanoic acid. So to do the percentage of oxygen, we just need to find the mass of oxygen and divide by the molar mass of the entire compound. So for the molar mass, it's the mass of hydrogen times 2 plus the mass of carbon plus the mass of oxygen times 2, which works out to be 46.03 grams per mole. Now, since there's 2 moles of oxygen, that'll be 32.00 divided by 46.03 because it's a percentage. You gotta multiply it by 100. I got a cheat sheet here with, I pre-did the test. I got all my answers here just so I don't have to punch numbers into the calculator too much. And that's going to equal 69.52%. That's a 9. It's a crappy one. So why 2 decimal places? Because everything had 2 decimal places. All right. Number 1, part C says methanoic acid and ethanal both have a carbonyl group and have similar molar masses. Explain why ethanol has a much lower boiling point. So you just have to identify the type. So methanoic acid can make hydrogen bonds. Ethanol only has dipole-dipole, and hydrogen bonding is stronger. So mark 1, mark 2. Part 2, II says, outline why ethanol and methanoic acid are both fully miscible. Miscible is just a, I don't know, synonym, homophone, I don't even know. It's another word for soluble. So water is a polar solvent, and both methanoic acid and ethanol are both polar. So they'll both dissolve in water, which is also polar. I would avoid terms like dissolves like, but that's really what that's about. All right, so III says predict, given the explanation, the relative electrical conductivity of the solutions of methanoic acid, ethanol, and hydrochloric acid. Well, remember, the more ions in solution, the greater the conductivity. So that means HCl will have the highest, then the methanoic acid, and then finally ethanol. Now, so why is HCl the highest? Because it's a strong acid, it fully dissociates. Methanoic acid is a weak acid, so it only partially dissociates. And ethanol doesn't really dissociate at all. Ionic compounds and acid and bases dissociate into ions when dissolved, but molecular compounds that aren't acids and bases generally dissolve just by being solvated. So ethanol does not produce ions, or it doesn't produce a lot. All right, so moving on, it says methanoic acid acts as a weak monobasic acid in aqueous solution. 2 liters or cubic decimeters of a solution of methanoic acid was prepared, and 25 cubic centimeters of it was found to require exactly 20.7 cubic centimeters of 0.1 molar sodium hydroxide. All right, calculate the mass of methanoic acid to use to make the solution. All right, so when we do this, I'm going to get my little cheat sheet out here, right? Turn to the appropriate page. Because it tells us that it's monobasic, that means the number of moles of the acid are equal to the number of moles of the base. Well, we are given a volume and a concentration of the base. Remember, if you multiply the volume in cubic decimeters by the concentration, it'll tell you the number of moles of what it is. But since everything's 1-to-1, it's also the number of moles of methanoic acid, but only in that 25 cubic centimeter sample. So let's go ahead and find the number of moles of methanoic acid in there. It's just going to be the volume of the base, which is in cubic decimeters, 0.0207, times the concentration, which is 0.100, which gives us 0.00207 moles, but that's moles for every 25 cubic centimeters. All right, so what I'm going to do now is just find out how many grams that would be. So grams of HCOOH would just be the number of moles times the molar mass, which was 46.03. When you do that, you get 0.0953 grams, but that's the number of grams for every 25 cubic centimeters. 4 times 25 is 110. That means in 2 liters, it's 80 times more. So all I did was, to get the mass in the whole thing, I just take 0.0953 grams and multiply by 80, because that's the number of grams in 25 cubic centimeters, and that is 80 times more. When you do that, you get 7.62 grams, and that's your answer. Determine the pH of the methanoic acid solution using section 21. Remember that if you want the pH of any weak acid, well, if you want the pH of any acid, you need the concentration of hydrogen ions, right? And for a weak acid, the concentration of hydrogen ions will be the square root of the product of the concentration of the acid, which in this case is methanoic acid, times the Ka value for that acid. So the number of moles is pretty snappy, pretty simple, right? So if I want the concentration of the methanoic acid solution, I need the number of moles of methanoic acid in the 2-liter solution divided by the volume. So I know that there are 7.62 grams of it in that solution. So to get the number of moles, we just have to divide by the molar mass. So when I do the math up here, it'll be 7.62 grams divided by the molar mass, which was 46.03, and then divided by the 2 liters of solution. So that gives us a concentration of 0.0828 moles per liter. So I've got that part. Now I need the Ka part. Now remember, Ka, because it's a logarithmic relationship, is 10 to the negative pKa. So section 21 gives us pKa values. For methanoic acid, I believe it's right at the top. Let me see if I got it there. I don't. It'll be 10 to the negative 3.75. Let me just open up my data booklets here. There we go. Yep, 3.75. Right, so that'll just be 10 to the negative 3.75, which equals 1.78 times 10 to the negative 4th. So now I just need to take the negative log of the hydrogen ion concentration. Well, the hydrogen ion concentration is going to be the square root of 0.0828 times the Ka value, which is 1.78 times 10 to the negative 4th. When you do that, you get the concentration is 0.00384, if I can read my writing over there. If I take the negative log base 10 of that, it gives me the pH, which is 2.42. Yay. And then part III says, predict using an equation whether the pH of this sodium methanoate solution would be greater than, less than, or equal to 7. So the sodium comes from a strong base. The methanoate ion comes from a weak acid. That means the pH will be greater than 7, because the conjugate of a weak acid, which the methanoate ion is, acts strongly basic. So to show the equation, we just want to show that methanoate ion, reacting with water to produce a basic solution. Well, if we're going to have a basic solution, then we're going to have hydroxide ions. We take the OH away from water, which leaves H+, which will react to produce the undissociated acid. So I got to say that's mark 01 and that's a mark 2. I bet you for that one, if you get it at all, they give you all the marks. Again, we'll see. All right, so part 4, IV, explain why the two carbon-oxygen bonds in the ion are of equal length and compare their length to the carbon-oxygen bonds in the methanoic acid. So what I did here just to illustrate this is I drew the structure of each. Remember, when the methanoic acid dissociates, that's the H that pops off, and that oxygen keeps that pair of electrons. That's where we get our H plus from, right? So here's the ion that's produced. Notice, ooh, you can move that double bond to and fro without rearranging any of the atoms. But you can't move that one there because that would give oxygen too many. So the reason why the lengths are the same, because this ion, because you can move the bond without moving the atoms, has resonance, and that equalizes the bond strength. So the bonds in the ethanoid ion will be a little bit longer than the double bond and a little bit shorter than the single bond. Make sure you say everything, because I bet you that's mark 1 and that's mark 2. I haven't checked the mark scheme yet. I like to, with these, to grade myself afterwards. I like to do the whole thing. So afterwards I will do that and I'll let you know how I did in class. All right, number 2 says methanoic acid can be produced by the hydrogenation of carbon dioxide according to this equilibrium. So there's our equation. Explain why the process has been extensively investigated in recent years. Well, climate change. Look at this. Gaseous carbon dioxide, which is a primary greenhouse gas, is consumed to make methanoic acid. So that will reduce carbon dioxide pollution in the air. Now, 2 marks here. I don't know if I was a bit which mitigates the effects of climate change. That would probably give you the 2nd mark, but I guess we'll have to see. That says state the equilibrium constant expression for this reaction. So remember, it's products raised to coefficients over reactants raised to coefficients. Everything has to be either gas or aqueous. So everything is 1 to 1 to 1 here. Everything's a gas. So the K expression, which would have a subscript of P because we're talking about gases here, would be the concentration, or in this case, the pressure of the gaseous methanoic acid divided by the concentration, or I guess the pressure of carbon dioxide times H2. Products over coefficients, excuse me, or over reactants. All right, so question number 2 here. Part C says bond enthalpies are a useful way of finding the approximate enthalpy changes. Determine the enthalpy change of this reaction using section 11. So if we look here, section 11 are the bond enthalpy values. What you really need to know is that when we're doing the bond enthalpy, the delta H we calculate is the sum of the delta H, the bond enthalpy for all the bonds broken, minus the sum of the bond enthalpies of all the bonds formed. So bonds are always broken in our reactants and formed in our products. So it's essentially reactants minus products. So to do this, we got to work out the type of bonds we have here. Just as a reminder, it's CO2 plus H2O making HCOOH. So everything is 1 to 1 to 1. So in 1 mole of CO2, I'm going to write small here so I can fit this. It's going to be 2 moles of carbon-oxygen double bonds plus 1 mole of hydrogen-hydrogen single bonds minus, well, in this molecule I have 1 bond between carbon and hydrogen, so the carbon-hydrogen bond, plus, that's a C double bond O, that's a single O, so plus C double bond O, plus CO, and then 1 for the OH at the end. Why I put some in parentheses but others not is a mystery to me. Anywho, now all we got to do is look up these values in table 11 and substitute. So it's 2 times C double bond O, that's 2 times 804, which is the bond enthalpy for the carbon-oxygen double bond, plus 436 for the hydrogen-hydrogen bond, minus 414 for that carbon-hydrogen, plus 804 for that carbon-oxygen double, plus 358 for the carbon-oxygen single, plus 463 for the OH. When you plug all those values in, you get 5 kilojoules per mole. Now, one thing I think they're going to do is, well, anyways, so this was all adding, right? So remember, the rules for sig figs when you're adding are to count the decimal places. All of these values have no decimal places. So that's why it's 5. You may be tempted to say 5.00, but 5.00 would not get you that mark because they want you to be within plus or minus 1 of the number of sig figs in the correct answer. Since there's only going to be 1 in there, making it 5.00 would not give you credit for that. But just remember your rules. All we did was add and subtract here. When you're adding and subtracting, your answer has to have the same number of decimal places as the numbers you added and subtracted. So that's why we get that. All right, so part II says assuming a 0.1% uncertainty for each bond enthalpy, determine the resulting percentage uncertainty of the calculated enthalpy change. So again, all we did is add and subtract here. So when we're adding and subtracting to propagate the uncertainty, we add all the absolute uncertainties. So if it's 0.1% for each, that means, ooh, the uncertainty is just 0.1. So all we got to do to get the absolute uncertainty is add the uncertainties of all the values we used. So there's 3 total 804s. So that would be 3 times 0.804. Right, 1% of 804 plus 0.436 plus 0.414. I already considered that 804, so plus 0.358 plus 0.463. When you do that math, you get 4.083. And then the percent uncertainty is just the uncertainty over the measurement. The uncertainty is 4.083 divided by the measurement, which is 5. Times 100 gives you 81.7%, but that is a measured 5. Only 1 sig fig, so that's going to round to 80%. All right, so part I says, bond enthalpies are usually only approximate values. Well, they're approximate values because they're averages, right? So it says which enthalpy that's used is exact. Well, it's got to be the hydrogen-hydrogen bond. Hydrogen can only make one bond, so this bond only occurs in the hydrogen molecule. There's no averaging required, so it's exact. Part D to number 2 says, suggests why temperature has a small effect on the value of K. Well, remember the enthalpy change was just 5. I said it was very close to 0, or it was small, or something like that would do it. All right, so moving on to part E, it says calculate the standard entropy change of the reaction using data from section 12. So if we look in our data booklet, section 12 is thermodynamic data or formation data, enthalpy, Gibbs free energy, and entropy of formation. So it gives us 2 values, probably because they're not on here. So if we look at our reaction, here it is. Oh, I'm not showing you my screen. Here it is right there, right there. All right, so we just have to do products minus reactants. How do we know? Because whenever it's table 12, the change in entropy will be the sum of the entropy of products minus the sum of the entropy for reactants. All right, so when we do this, it's going to be products minus reactants. There's only one product, methanoic acid, so it'll be 251.0 minus the sum of hydrogen and carbon dioxide. Well, hydrogen is 130.7 plus CO2, which in the data booklet tells us it's 213.8. When you do the math, you get negative 93.5 kilojoules per mole. Know how to do those because the math is not really difficult, right? So know how to do them for sure. Question number 2, moving on, says the conversion of carbon dioxide to methanoic acid is usually carried out over a catalyst. Sketch on the axes provided energy profiles for the reaction with and without a catalyst, indicating delta H and the activation energies. All right, so this is an endothermic reaction. So when we do our graph, we want to show our products having higher enthalpy than our reactants. Since they wrote the reactants here, I'm going to write the products here just to be safe. Now the difference between the enthalpy of reactants and products from here to here is delta H. From the peak of the hump to the energy of reactants is activation energy. And adding a catalyst doesn't change anything except for the activation energy. So from here to here is the activation energy with a catalyst. So 3 marks, I'd be willing to bet 1 mark for that, 1 for that, and 1 for the actual shape. All right, so then it says state 1 change, other than carrying out the reaction over a catalyst, that would increase the rate. Well, think about things that can increase rate. Concentration. If they're gases, we could change pressure or add a catalyst. Well, we can't add a catalyst here because we're told we can't. But if we look at the equation, if I can find the equation, I'm really bad at this. There we go. Ooh, I've got 2 moles of gas here and 1 there, which is why we could increase the pressure. Part G says determine the oxidation state of carbon and methanoic acid. So here is methanoic acid. Remember, hydrogen and oxygen have rules. Hydrogen's always +1 and oxygen's always -2. Now when we add up all the oxidation states here, they have to add up to 0. Since there's 2 hydrogens, it's a total of +2. Since there are 2 oxygens, it's a total of -4. So -4 + 2 is -2. That means carbon has to be +2 to make the compound neutral. Number 3 starts with methanoic acid can be converted into methyl methanoate. Ooh, carboxylic acid with an alcohol. State the name of the reagent and catalyst. So we would use methanol to give us that. And the catalyst is sulfuric acid. All right, so part B. Oh, wait a minute. I don't think I finished a problem over here. Oh, no, I did. I don't know why I thought that. Whatever. All right, so 1.72 grams of methyl methanoate product is produced from 2.83 grams of methanoic acid and in excess of the other reagent. Determine the percent yield. Let me just get up here to my dingy. So might help you to write out a balanced equation, but everything here is 1 to 1 to 1. It's telling us we started with that. So the first thing I got to do is find out the number of moles of methanoic acid. So to do that, I take the mass of methanoic acid, which is 2.83, and divide by the molar mass to give us the number of moles, and that is 0.0615 moles. Now the percent yield is just the experimental over theoretical. Well, that's my theoretical in moles, but remember, if everything's 1 to 1, that's also the number of moles of the product that's formed. So all I have to do is multiply by the molar mass of methyl methanoate, which is 60.06, and I get 3.69 grams should form. That's my theoretical yield. That's my experimental. So the percent yield, it will be 1.72 divided by 2.83 times 100, which equals 46.6%. This is just a stoichiometric problem. All right, so part C says the conversion of methanoic acid to methyl methanoate can be followed by changes in spectra. State 1 similarity and 1 difference you would expect in the infrared spectrum of these 2 compounds using section 26. So if we go to section 26, that's our infrared data. Now, one thing they'll both feature is the carbon-oxygen double bond, because both in the carboxyl group and in the ester, you have your C double bond O. But one thing the carboxylic acid will have that the ester does not is the OH absorption for the hydrogen bonding in the acid. So for the similarity, both will have the carbon-oxygen double bond absorption between 1700 and 1750, but only the methanoic acid would show, or it shouldn't be HC, it should be HCOOCH3 would show the absorption. Oh wait, no, derp. Trust your thinking, man. Only the acid would show the absorption for the OH. Trust in thyself. All right, so question number 3 to II. Removed for copyright reasons. This is deduced referring to the integration trace, whether the NMR spectrum is methanoic acid or methanoate. methylmethanoate. Well, because you got HCOH, in each case they have two environments, but this would be 1 to 1, and that would be 1 to 3. And then state the class to which methylmethanoate belongs. I already mentioned it. It's an ester. All right, question number 4 says carbon disulfide undergoes gas phase hydrolysis according to the overall equation. So there's an equation there. Calculate the enthalpy change of the reaction from section 12. All right, so we're going back to section 12 here. We're given two values. I suspect that the other two values aren't given to us because they're in the table. All right, so I'm going to write those values up here. So for steam, when you look, it's negative 241.8. And for carbon dioxide is negative 393.5. Yeah. So if it's table 12, it's always products minus reactants. Don't forget, though, these values are per mole, and the coefficients tell us the ratio of moles. So when I'm calculating delta H, I got to get the sum of the enthalpy of formations of my products. So it's going to be negative 393.5 plus 2 times that for hydrogen sulfide, which is negative 20.6. I'm then going to subtract the enthalpy of formation of carbon disulfide, which is 88.7, plus that for water, but that 241.8 is for 1 mole, so 2 times negative 241.8. When you do the math there, you get negative 39.8 kilojoules per mole. Sorry, I haven't been paying attention to the screen, so if things are going off, I'm sorry. Outline why you would expect the entropy change to be small. Remember, entropy is all about the number of particles. I got 3 moles of gas there, 3 moles of gas there. Equal moles of gas is probably the best answer. We shall see. Neglecting any entropy change, use your answer to part A1 and section 1 and 2 of the data booklet to estimate the equilibrium constant at 500. All right, so we're going to have some major maths here. Now, before we begin, the equation from section 1, the first one anyways, will be the delta G equation, which is delta G is delta H minus T delta S. So it says neglecting an entropy change. That means the entropy change is essentially 0. If it's 0, this whole factor is 0, so delta G will be equal to delta H. So the equation we use to connect delta G to the equilibrium constant is delta G is equal to negative RT times the natural log of K. Now remember, R here is in joules. That is our delta G, which is in kilojoules. So I'm going to convert to the R version. Okay, so when we plug in all the values, delta G, well, first of all, let's solve for K, right? So it's going to be the natural log of K will be equal to delta G theta divided by RT, all multiplied by -1, not minus. All right, so when we plug in, I'm going to plug my delta G in kilojoules. Notice it's negative. That will cancel out that negative factor. So 39.8. And then divided by R. Remember, R is in joules per mole K. So to get R, we have to do, in the right unit, we have to do 8.31 times 10 to the minus third times the temperature, which is 500. When you do this, the natural log of K turns out to be equal to 9.58, and K will be equal to E to the negative 9.58, so K will be 1.45 times 10 to the fourth, which means the forward reaction here is most definitely favored. Moving right along, just to keep things snappy. The concentrations of the species involved in the equilibrium are, so we're given equilibrium concentrations, X and 2X. Calculate the numerical value of X, the concentration of carbon dioxide at equilibrium, using your answer from 4A3. So essentially what we are given, here are some equilibrium concentrations and we need those. So we can easily get our K expression. Our K expression will be concentration of CO2 times the concentration of H2S squared. Again, these are just coming from the equation. I'm not going to flip back to it. CS2 times H2O squared. All right, so K is 1.45, right? 1.45 times 10 to the fourth, and that will equal x times 2x squared, divided by 0.0400 times 0.100 squared. All right, so when this combines, we're going to get 4x cubed. All right, so x cubed essentially will be equal to 1.45 times 10 to the fourth times 0.0400. 0.1 squared is 0.0100 divided by 4. So x cubed will equal 1.45. So to get the value for x will be the cubed root of 1.45, right, which equals, I don't know, what does it equal? I don't have it on my cheat sheet here. So where's this button? I think it's math. Cubed roots. The cube root of 1.45 is 1.13. So that's our answer. All right, then it asks to deduce the molecular geometries of these two compounds. CS2, just like CO2, is linear, and H2S is bent. Remember, the reasoning has to do with electrons on the central atom. So H2S has 2 pairs of non-bonding electrons on the sulfur. CS2 has 0 on the carbon, I think. Boom, boom, and that's probably another mark. It's probably like an and situation. Again, we'll go over the Mars scheme in class. Moving right along, it says sulfur has a number of natural isotopes and a sample of sulfur was enriched in sulfur 36 to produce a mixture with the following composition. Calculate the relative atomic mass of this enriched sample, corrected 2 decimal places. So remember, to find the relative atomic mass of anything, you have to take the mass of each isotope and multiply by its natural abundance. So when we set that up here, it's going to be the first isotope, which is 32, times its abundance, which is 0.90, plus sulfur 33 times its abundance, which is 0.01, plus sulfur 34, which has a mass of 34, times its abundance, which is 0.04, plus sulfur 36 times its abundance, which is 0.05. When you punch all these values into your calculating machine, you get 32.29 grams per mole. In naturally occurring sulfur, the relative abundance of sulfur 36 is only 0.01%. Calculate the number of atoms of this isotope that would be present in 1 gram of natural sulfur. So this is actually pretty snappy, right? All we got to do is figure out the number of atoms in total and then multiply it by 0.01%. So I have 1 gram of sulfur. To find the number of moles, I'm going to divide by the molar mass, which gives us 0.03118 moles. Now what I'm going to do is multiply this. You could multiply this by 0.01%, which would be times 0.001. Let me 0.01. Yeah, times 10 to the fourth, so 0.0001, and that gives us 3.118 times 10 to the negative 6th moles of just that isotope. Because this is the number of moles total, but we only have 0.01%, so when I multiply by 0.01%, I get that. So then all I got to do is take that 3.118 times 10 to the negative 6th and multiply it by Avogadro's constant. And when you do that, you get 1.88 times 10 to the 18th atoms. Another way you could have done it, you could have just multiplied that by Avogadro's number and then multiply the answer by 0.01%. Either way, you're going to come out with that as your answer probably. Number 5 says beryllium is a low-density metal that is used in specialized lightweight alloys. State the technique used to determine the crystal structure. That's X-ray crystallography. Outline the electrostatic attraction in the beryllium crystal. So it's basically asking you to outline electrostatic attraction in a metal. So that's always going to be electrostatic attraction between the lattice of, in this case, beryllium cations and delocalized electrons. All right, moving right along, we have an electrolytic cell diagram here with molten BaCl2 as the electrolyte. Why is it used as an electrolyte? Because when any ionic compound is in the liquid form, their ions are mobile, which makes them conductive. Number 5II says identify the electrode at which beryllium will produce and the polarity of that electrode. So remember, beryllium ions are positively charged. To form the beryllium metal, they have to gain electrons, which is reduction, which is why it's the cathode. And remember, the electrolytic cell is the bizarro world where the cathode is negative, because it has to be negative to attract those positive ions. III says write a balanced equation for the reaction occurring at the other electrode. So the other thing we had there was chlorine. So in that case, molten chloride ions are going to be oxidized into gaseous chlorine gas, right? So I got to go ahead and balance the chlorine atoms. Over here I have a total of -2 charge, so that means we're going to form 2 moles of electrons. And then finally, calculate the mass of beryllium that would be produced by the passage of 1.00 times 10 to the 6 coulombs of electrical charge. When I first saw that, I was like, I have never seen one like this before. But if we look at section 2, all I did was look for something that had coulombs in it. Ooh, there's Faraday's constant. Well, if I'm given coulombs and I divide by Faraday's constant, which is coulombs per mole, oh, I'm writing here and not, and you do all the math, the coulombs will cancel and you'll be left with a unit of moles. Well, if we want the mass, knowing the number of moles is useful. All right, so we have 1.00 times 10 to the 6 coulombs. Faraday's constant tells us that there are, what is it, 9.65 times 10 to the 4th? Cheat sheet. 4.69, hold on, let me just look, because that 4 looks like a 9. 9.65 times 10 to the 4th. Okay, so divided by 9.65 times 10 to the 4th, and that's going to give us, let me actually just do it. 1e6 divided by 9.65 e4, it gives us 10.4, but that's moles of electrons added. Now remember, beryllium needs 2 electrons, right? So we've got the number of moles. If we multiply it by the molar mass of beryllium, which is 9.01, that gives us 10.4 times 9.01, 93.70 grams. But remember, it takes 2 moles of electrons to produce 1 mole of beryllium. So we got to divide that by 2. And that divided by 2 gives us 46.9 grams. Tricky. It's 2 marks. You probably get 1 for that. And then the second one for that. A lot of kids are probably going to give this as the answer because they don't consider that. All right, moving right along. Boy, these paper 2s are taxing. Beryllium forms a chloride, BeCl2. Draw the Lewis structure. Okay, so remember beryllium in group 2 has 2 electrons to donate, and each chlorine atom has 7. So we're going to have our beryllium in the middle, forming bonds to chlorine with the dots all around chlorine. So again, beryllium shares 1 electron there. It shares another one with another chlorine, and that's where we get that structure. Outline how the Lewis structure differs from most. I would say that beryllium has an incomplete valence shell. Because beryllium wants 8, just like anybody, right? It typically loses electrons being a metal, but it's sharing them here. So, all right, so beryllium chloride partially dimerizes, which means they combine to produce this molecule. Identify the hybridization of the beryllium. Oh, there's 3 domains around it, so that makes it sp2. Easy peasy. All right, so to describe the interactions between the BeCl2 monomers to form the dimer. So again, if something donates a pair of electrons, it's a Lewis base. If it gains, it acts as a Lewis acid. So chlorine is the Lewis base, beryllium is the Lewis acid. Iron 3 chloride also exists as a dimer in the vapor phase, but iron, unlike beryllium, is a transition element. Outlined in terms of electronic structure, what identifies a transition element? It means they have an incomplete outer d sublevel. Remember, they also have multiple charges, but that's mentioned here. So according in terms of electronic structure, it's about the fact that they have incomplete d orbitals. The first 4 ionization energies of beryllium and iron are shown, with the beryllium being the dots. One common property of transition elements is that they have variable oxidation states. Discuss referring to this graph why iron but not beryllium displays this characteristic. So I'm seeing 3 marks here. I'm going to say beryllium can only make, I'm going to say a +2 ion. The reason why the third ionization energy is too high to remove a third electron. Okay, but if we look for iron, so I'm going to say in iron, successive ionization energies are, I'm going to say more gradually increased, I guess. And then for the third, I'm going to say iron can lose more than 2 electrons before the large jump. I don't know. Again, we're going to have to look at the Mark scheme. I don't know if I got them all. I mean, those are all true statements. But if we look here, after the second one, that beryllium loses, boom, we get a jump. But there's no jump. We'll see. All right, the standard, oh, my hand is killing me. Shake the hand, shake the hand. The standard electrode potential of beryllium ions to beryllium is -1.85. Calculate the cell potential for this reaction. So the cell potential will just be the reduction potential for what is reduced minus the reduction potential for what is oxidized. So here we got beryllium being oxidized, water being reduced, hydrogen in water being reduced to form hydrogen. So it'll be water being reduced. Let me just find this stupid value. All right, so that is -0.83 minus that for beryllium, which is -1.85. When you do all the math, it gets 1.02 volts. And then it says deduce, giving a reason whether this reaction is spontaneous. Yes, it's spontaneous. Yes. And the reason, well, we could look at this equation, NFE, right? If E theta is positive, then delta G is negative. And if delta G is negative, you're spontaneous. All right, continuing question number 5. It says explain in terms of nuclear charge, electron subshells, and the shielding provided by filled electron shells why the first ionization energy increases from lithium to beryllium, but decreases from beryllium to boron. So this is 4 marks. To save time, I'm just going to show you what I wrote up here. The nuclear charge increases as you go from lithium to beryllium to boron. All right, so for lithium to beryllium, you have an increase in the effective nuclear charge, same number of occupied shells, and the same shielding, which is why it's harder to remove the electron from beryllium. But from beryllium to boron, you get shielding from that full 2s sublevel, which lowers the ionization energy for boron. I really feel like I only said I guess I said that. I said same shells, same shielding by the 2s. I may have gotten 4, but we'll see. Outline how first ionization energy could be found from the atomic emission spectrum. Remember the convergence limit, n equals infinity. You got to find the frequency at it. I don't know why I said convergence stability, but whatever. All right, phenylethanone is a fragrant compound that occurs naturally in fruits such as bananas and apples. So the phenylethanone may be synthesized in a two-stage process from phenylethene. So we got it. This is essentially an alkene with just a phenyl substituent. We got water and sulfuric acid, which means X is going to be an alcohol. We're then going to react the alcohol to form an aldehyde. Ooh, so draw the structural formula of the intermediate. Okay, so remember, all alkenes do electrophilic addition. And in each case, the double bond breaks, and each carbon can bond to one more thing. So the one more things in water are the two parts of water. So H and OH. Now, you got to think major versus minor product, right? We need to have X be the major product, so we have to consider, that would be a secondary carbocation. That would be primary. Secondary is more stable. So when we draw our substance, this all stays the same. That's a nice hexagon, right? Here, we're going to keep this hydrogen and make the OH there, giving us just a methyl group over here. So, I mean, I don't know why I drew all the H's out like that, but I guess if I drew some, I better draw all. And there you go. So we got the secondary alcohol. So outline why X can be exhibit stereoisomerism, because that carbon is chiral. It's bonded to an OH, an H, a methyl group, and a phenyl group. All right, so if you're bonded to 4 unique things, that means you're chiral. All right, so state the reagent required for the second synthesis B. So alcohol to aldehyde is oxidation. So you could either use potassium dichromate and water, or sodium dichromate, some dichromate salt, or some permanganate salt. So potassium permanganate or whatever. Determine the compound that will be formed as the minor product. Okay, so if that's the major product, the minor product would have the carbonyl there, right? So what happens to this? The OH goes there, and the H goes there. So I'm going to just draw it out to be safe. So if that were the case, in this step, this would have bonded to the hydrogens, and this carbon would have bonded to the O, so we're going to make the aldehyde over there. Determine the compound that will be formed in the two-stage and outline why this will occur. I'm going to say the secondary, see how I saw the 2 marks? Secondary carbocation is more stable. Yay. Ooh, almost done. Thank Jeebus. All right. Finally, when heated with a mixture of concentrated sulfuric and nitric acids, phenylethanone is nitrated in a similar manner to benzene to form 3-nitrophenylethanone. There it is with our NO2 group down there. Write the formula of the electrophile produced in the mixture. Well, whenever we're nitrating a compound, we use the nitronium ion, which is NO2 1+. And explain the mechanism of the reaction between phenylethanone and the nitrating agent using curly arrows to represent the movement of electron pairs. Very important to note that if that's where the NO2 group is going to attach, that's what we got to show. So we've got our phenyl group here with that up top. So the first thing that happens is our electrophile comes in and electrons go from the ring to that. That's going to produce this intermediate. Everything stays the same except for the bond that's formed. So we got our carbon action double and our methyl up here. Uh-oh, I already made a mistake. Slow down there, champ. So carbon, oxygen, CH3. I did the full ring here. Remember, in the intermediate, you have to show the partial disruption of the aromaticity and the positive charge. Okay, we're going to show our electrophile added here, as well as the H. And remember, our old friend water is going to deprotonate. So these electrons go to the hydrogen, and these electrons go back into the ring. And then the final product will just be the nitrated aldehyde. So the aromaticity is back. We got our nitro group down here. And all that up there. This is like, know the pictures, kiddos, know the pictures. I can't really explain it any better than that. And finally, chemists have a rule of thumb that raising the temperature by 10 degrees doubles the reaction rate. Deduce the activation energy, assuming that a rise in temperature from 25 to 35 doubled the rate of reaction. Use sections 1 and 2 of the data booklet. So there's section 2. Why do we need section 1? It's going to give us an equation we've never used before. Ooh, the effect of K at 2 different temperatures. All right, so cheat sheet for Schurzy. So when we use this equation, or any equation that involves R, we have to convert the temperatures into Kelvin. All right, so the initial temperature I'll call T1 was 25, which is 298 Kelvin, which makes T2 10 degrees higher, 308 Kelvin. So the equation we use is the natural log of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. So this is just a bunch of annoying pluggy and chuggy. All right, so I'm just going to solve for activation energy here because that's what we're calculating. So that will be R times the natural log of K1 over K2 divided by this factor, so 1 over T1 minus 1 over T2 minus T1, sorry. So now let's go ahead and plug in the values. All right, so again, we got to beware of our R. So R here is, I'll use the 8.31. That means when we calculate activation energy, it'll be in joules. All right, times the natural log of K1 over K2. Well, we're not given K1 and K2, but if K1 goes with T1 and K2 goes with T2 and it doubles, we can just assume that it's 0.5 because that would be 2, 1. And then we're just going to divide by 1 over T1, which was T2, excuse me, which is 308 minus 1 over T1, which is 298. When you plug the numbers into your calculator, you get 52,868 joules per mole. We need kilojoules per mole. And for sig figs, sig figs are all wild here. I don't even know. I'm just going to say equals 53 kilojoules per mole. That's it, kids. Whoa. I don't even know how much time is on this video. Probably too much. So I'll stop it here. Thank you so much.